Welcome to the topology class. We are going to talk some more about homeomorphisms today. I would like to discuss some more things about homeomorphisms, some more examples that are interesting to see about homeomorphisms. So maybe we'll refresh our memory about the definition. A function. So if I have f going x to y, this is a homeomorphism when it means f is a bijection, f is continuous, and also f inverse is continuous. All of these things must be true to be a homeomorphism. All right, I'll put the comma there. The Oxford comma is what I'm into it. That's what it means to be a homeomorphism. And if there is a homeomorphism from one topological space to another, then we consider them to be the same topological space. All of the properties that we care about in topology will be the same from one to another. Well, most of them at least. So in this case, then we say x and y are topologically equivalent. Topologically equivalent, or homeomorphic is what I'm usually going to say, although our book usually says topologically equivalent. All right, and actually there's a notation for this, which I don't think that I wrote this last time, but like this. It's like the triangle congruent sign, I think, from geometry. It doesn't mean that because actually, if you're talking about homeomorphisms, actually all triangles are homeomorphic to one another, regardless of their angles or how big they are or whatever. So it's not the same as congruence in geometry, but we use that symbol to mean homeomorphic when it's clear. All right. So what we talked about last time, I want to talk about the general question of like, what kinds of things are homeomorphic to other kinds of things? So what we discussed last time was in R with the standard topology, intervals of various types are homeomorphic to other intervals of the same type. So in R with standard topology, last time we demonstrated that any open intervals are homeomorphic. Any one open interval is homeomorphic to any other open interval. Also, any, I'll say to each other, right? If you have two open intervals, they will be homeomorphic to each other. I mean, like bounded open intervals, not stretching out to infinity. That's something we need to talk about. But bounded open intervals are homeomorphic to each other. Also, any closed intervals are homeomorphic to each other. And also, any interval having one point but not the other is homeomorphic to any other. And it doesn't matter if it's the left or the right endpoint because there are homeomorphisms that flip it over. So also, I will just, to be clear about it, any interval like, say, A to B, or the other way around, A to B, but including the right endpoint, those are all homeomorphic to one another also. Any half open interval are all homeomorphic. All right. We consider all intervals in topology are basically the same. It does matter which of the endpoints they include, but it doesn't matter, say, how big it is, like how you can stretch them out by a homeomorphism or move it around along the number line. It doesn't matter where it is situated. All right. But what I want to talk about today, at least at the beginning today, that's not horribly, not going to take forever to discuss this. What about unbounded intervals? Where do they sit in this? That is, intervals which go out to infinity on one end or the other, or perhaps both. That would be all of R. All right. What about unbounded intervals? Actually, it turns out, so this is a little bit surprising. All of R is actually homeomorphic to a small open interval. So it turns out, I don't know if this is what you were expecting or not, all of R is homeomorphic to any bounded open interval. Like, for instance, well, I can just write it this way. R is homeomorphic to the open interval from A to B. Even though R is infinite and A to B is, I should say, unbounded. R is unbounded, but the interval A to B is bounded. They are still homeomorphic. It is possible to stretch down all of R, which is unbounded. You can still stretch it down with a function into a bounded interval. I don't know if this sounds surprising to you, but actually, I'm sure you have seen examples of functions that do this sort of thing. And I can tell you specifically a function. Here is an example. How about f of x equals, you probably didn't expect me to mention this today, arctan of x. This is an old favorite from calculus. Anybody happen to remember what the graph of arctan looks like? Yeah?
Doesn't it look like a backwards S?
A backwards S.
And there's like asymptotes on
Yeah. He's giving me various hand gestures, which is about as good as I could expect when asking somebody what the graph of arctan looks like. If you recall, the graph of tan looks like this, which has many asymptotes, right? When you look at arctan, you can only invert one of those because this tangent is not one-to-one. So you choose this bit of it, and you invert it by sort of flipping it along a 45-degree line. I hope you have a vague memory of this. It's not important if you remember all the details here. But the graph of arctan looks like this. And it has horizontal asymptotes, and if you recall why those, the original tangent has these asymptotes because tan is sine over cosine, and cosine equals 0 every so often. These vertical asymptotes turn into horizontal asymptotes here. What? Anyone remember what the values are of those asymptotes? Doesn't really matter, but they're pi over 2 and minus pi over 2. All right. So I could write the arctan. So here, f of x, its domain, we don't put the x in there. The domain is all of R, right? Because you can plug any real number in. What is the codomain, or the range more specifically? It's not all of R. I mean, the codomain is all of R, but you don't get all the real numbers out of this, right? You only get the interval minus pi over 2 to pi over 2. All right? And you can tell by looking at the graph that f is a bijection, right? Because it's onto, it's not onto the whole real number line, but it is onto this set. Right? Every value in between negative pi over 2 and pi over 2 is achieved by the function as a y value. And also it's one-to-one because of the sort of horizontal line test, right? So this f is a bijection. And it's also continuous. Everybody knows the arctangent function is continuous. You can tell by looking at the graph. And the inverse is also continuous. The inverse of the arctangent is what you get if you were to again flip this graph back sort of the right way up. And then that's also, continuous. It's still continuous. So this is a bijection, and f inverse are continuous. All right. So the moral of the story is that means f is a homeomorphism. And so f is a homeomorphism. So that means R is topologically equivalent to this open interval, minus pi over 2 to pi over 2. And therefore, it's equivalent to any open interval, because the open interval pi over 2 to pi over 2 is equivalent to all the other open intervals, like we talked about last time. So R is homeomorphic, or topologically equivalent, if you prefer, to any open interval. All right. A little strange in my opinion, just because R, to me, R really does look kind of different from a bounded open interval because R is unbounded. But from a topological point of view, they are the same. Because basically, what's important about the open interval is kind of like it doesn't have boundary points. It consists of a bunch of things in a line with no thing on the end of either end, right? And if you think about it, R is the same way. It's a bunch of things in a line, and there's no thing on the end on either side. So in that sense, they are kind of the same thing. They are definitely not geometrically equivalent because R is sort of much, much bigger as a geometrical thing, but topologically they are equivalent. All right. Yes?
Is this the same as like in real analysis saying the cardinality is the same? Like
Not quite the same, although this is a good thing to think about. It is true though that R and this have the same cardinality, but just because they have the same cardinality does not necessarily mean they're homeomorphic. Like in order to have the same cardinality, all you need is a bijection. Because that's how you show two sets have the same cardinality, is if there's a bijection from one to the other. So that's part of being a homeomorphism, but homeomorphism also requires this business. So any homeomorphism automatically means the two sets have the same cardinality, but it also means a little bit more. Like there are uncountable sets which are not homeomorphic to R. And we will actually later on today, we'll see some examples. All right, R is homeomorphic to any open interval. Okay, let's talk about, I should say bounded open interval. Let's talk about sort of a interval that's unbounded on one side. What about that? Is that also the same as R? What about, say, R versus something like that, the open interval 0 to infinity. Do you feel like those are the same topologically or different topologically? You want to vote just to get a sense of the feel of the room? What do you think? Are they the same? Give me the thumbs up if you think they're the same topologically, or the thumbs down if you think they're different. Or maybe you have no opinion. The way that I think about this, in the spirit of this, I saw some tentative ups, no downs, and some no opinions. In the spirit of this, I said the way that I think of these things topologically is that there are a bunch of things in a line with no thing on either end. So in that sense, these are the same. R consists of a bunch of things in a line with no thing on the other end, on either end. What about this? Well, I would say also this looks like a bunch of things in a line with no thing on either end. All right, so this, I feel like these should be equivalent to one another. Now, let's see if we can actually demonstrate a function which demonstrates their equivalence. So what we would need is, we need a function f which goes R, and its codomain is 0 to infinity. Maybe we could just try and think about, is there such a function that does that? I'm going to try to draw a graph of it. Can you imagine drawing a function? I don't care about if you know like a formula for this function, but can you imagine drawing a function where the domain is all of R, but the range is only the positive numbers? Yeah? Okay, here's a good idea. The absolute value. I have two problems with that, but it's a good thing to think about. Anyone have any problems with this? This is a good idea. The domain is all of R. What about the range here? Yeah? Yeah, so one problem I have with this is this includes 0 in the range, which we don't want, because we want this to be, although, maybe this will work for the next example that I'm about to talk about. But my other more serious problem with this is that is not a bijection. This is not 1-to-1. It's like 2-to-1 everywhere. So you need, I don't know, can you think of a way of maybe modifying that graph, or perhaps just coming up with a completely new one where it, first of all, never hits the axis and also is one-to-one. Yeah.
E of x.
Yeah, how about e to the x, he said. I think that'll do it. If you recall, the graph of e to the x looks like that, right? And this actually has all the properties that we want. So here, we're going to use f of x equal e to the x. And it just, I mean, everything we want to be true of this function is actually true. Actually, I mean, this is not the only function you could have used, although that's the one that I was going to pick. I don't know if there's a more natural one to use than that. F of x equals e to the x. So this is continuous with continuous inverse. The inverse is the natural log, which is also a continuous function. Everybody knows, all right? And it is a bijection if you use this as the codomain, right? 0 to infinity, it's a bijection. If it's not a bijection to all of R because you missed the negatives, but we're trying to miss the negatives anyway, so this is great. All right, so anyway, so this is a homeomorphism. So that means R is equivalent to any interval with an infinity on the top, all right? It's also, you can make one which gives you only negatives, right? So actually, if I wanted to get only the negatives, I could do that same function, but do it down here. That would be negative e to the x. It's the same as that, but all negative. So that one, can I just say, and R is also topologically equivalent, homeomorphic to minus infinity to 0, right? This is, to do this one, I use f of x equals, not e to the minus x, minus e to the x. That gives me all negative answers, all right? And then the range of that will be all the negative numbers, not including 0. Okay, so R is homeomorphic, and of course, you don't have to start at 0 here. If you wanted to do like 1 to infinity, you would use e to the x plus 1. That shifts the entire graph up by 1. So really, any open interval, so we can say R is topologically equivalent to any open unbounded interval like that. And also, if the infinity is on the other side, right? By using a negative. What about if they're both infinities? Is R homeomorphic to that? Yes, that is R. So yes, it is homeomorphic to that if they're both infinities. All right, great. Any thoughts about this? Okay, what about, I'm full of these what abouts. What about a unbounded interval, but the real endpoint is closed, like you include one endpoint? What about, I'm talking about something like 0 to infinity, like that. You want to show me the thumbs again? Do you think that this also is equivalent to R or not? Someone was giving me the fist. They were about to go up or down, but didn't quite make it. Remember, the general way I think of these things is this is a bunch of things in a line, but it doesn't have anything on the end, on either end, right? That's how I think of R in a topological sense. Is a bunch of things in a line, but it doesn't include any endpoints on either end. To me, this is different. This is a bunch of things in a line, but it has one endpoint, but not the other one. So actually, to me, it seems like this should be, it should be true that like the interval 0 to infinity is actually equivalent to one of these, right? Those seem to me that that should be the case. Let's try and think of a function that makes that happen. So you need a function, if I'm going to make this happen, you need a function where the domain is only 0 to infinity. So you can plug in 0 and any number greater. Actually, you know, it's a little easier to do this the other way around. So I'm going to try to make f go 0, 1 to 0 infinity. You can do either way, but to me, this one is slightly easier to draw the picture of. You know, I changed my mind. It's better the other way. Whatever. Let's stick with this. It doesn't matter. They're both. So the domain is 0 to 1. That means I'm not considering any of the negative x values, and I'm also only going up to 1, but not including the 1, right? So when I draw the graph, it's going to fit only in there. And also the answers should include 0, but and go up forever, but not down at all. So the answers, really the entire graph has to live inside that little strip there. Can anyone think of how you could make a graph that actually does this? This one I don't think you'll be able to tell me a formula for, but any idea about this? Your graph, its domain has to be this, not including that point, and its range has to be everything. If I were to draw such a graph, you have a suggestion? Yeah, how about a vertical asymptote on the number 1? I mean, that's a good idea. It has to, your graph has to go up forever, and it has to approach but not reach 1. So I think that's a good situation for putting a vertical asymptote at 1, like this. And then what should the rest of the graph look like? Well, first of all, when it comes to drawing the graph, I'm going to put a point right there, right? Just because of the way that the domain and the codomain have to work out. You probably should begin your graph right there. And then, I guess, just go up and approach the asymptote. So, something like that. You should ask yourself, is this really, well, it is continuous, right? I mean, it looks continuous at least. Is this really a bijection? Is it 1-to-1 and onto? I think it is. It's 1-to-1 because you have this like horizontal line only passes through one point at a time. And is it onto? What it's onto is this. Do you actually get all of the y values here out of the function? And the answer is yes. It does all the y values. Eventually hits any real number here. So this is that one that I drew there. This is a bijection with continuous and continuous inverse. I didn't say that very well grammatically. We don't really say with continuous. I should have said this is a continuous bijection with a continuous inverse. All right. Now it is a little unsatisfying maybe because I didn't write a formula for that. Topologically speaking, though, usually we don't like to write formulas for things in general just because it's not really necessary. I hope that you're convinced that there could be a function that does that. Although in this case, actually, it's fairly easy to come up with a formula of that because I will just bring to your attention, this is a piece of tangent of x. All right, if you look at the graph of tangent, it does exactly that, what you want it to do. All right, and so if I only consider, say, forget about everything out here. If I only consider that piece, then that piece right there, so this is called the, I think this word appears on your homework. I don't know if you're familiar with this, but this is called the restriction of tan x. It means you take the function, it is the function tangent, but I only consider a little piece of the domain. The restriction of tan x to the domain. Now it's not 0 to 1. That's the only difference from the one that we drew before. It's 0 to pi over 2 just because that's where tangent goes. But the restriction of tan x to 0 to pi over 2, sorry, I need the open on the pi over 2 side. This makes a homeomorphism that goes 0 pi over 2 to 0 to infinity. All right, so if you insist on writing formulas for everything, then you can use the tangent for that. If you want it to be 0 to 1, you could use tangent of x times 2 over pi. That would rescale the x values to make it go to 1, but I don't care about that so much. All right. So the moral of the story, I'm going to try and summarize all of these random, homeomorphisms that we've talked about so far. So in R with the standard topology, there are certain, categories of homeomorphic sets. They would include, so one category, I'll put them in sort of like a bracket, would include R, all of R. This is equivalent to open interval, say 0 to 1. I should just say, any open interval, A to B. And this is also equivalent to any unbounded open interval, A to infinity, and this is also equivalent to unbounded interval the other way around, right? All of those things are homeomorphic to one another. There's also the closed intervals, and that would be just that. Actually, that was not equivalent to anything else that we've talked about, and it is not equivalent to R because it does include both of the endpoints, and it's also not equivalent to one of those unbounded ones with only one endpoint. And then the third category would be something like this, A to B with only one endpoint, or A to B with the other endpoint, or A to infinity, or minus infinity to A, like that. All right. So when it comes to intervals in R, there are basically 3 categories in terms of what things are homeomorphic to one another. All right. And it turns out, although we have not demonstrated it, these categories are actually different from one another. Now that is actually quite a bit harder to show, but for example, R is not homeomorphic. Maybe I'll just write it with this thing. R is not homeomorphic to a closed interval, although that is more difficult to demonstrate. To show something is not homeomorphic, you have to show that no possible function can exist from one to the other, which is a continuous bijection with continuous inverse. And that typically is a harder thing to do. You would have to somehow consider all possible functions that you could make and then demonstrate that none of them are continuous bijection with continuous inverse. So I will say this is, it is true, these are not homeomorphic, but at this point at least, hard to prove. Actually, later on in the class we will talk about proving this. It's not so hard, it's just we haven't talked about the necessary ingredients to prove this. All right. Great. One little technicality that we need to discuss about homeomorphisms, and this is something actually that I have been assuming all along but never actually said, and I don't know if any of you have been thinking in the back of your mind, objecting to the way that I've been talking about these things. But something that I have been assuming all along is that you can make sort of categories of homeomorphic sets. That is to say, all the sets in the universe, you can just think of certain ones are equivalent to the other ones, and certain ones are not equivalent to those other ones. What I'm saying is that all sets can be divided into equivalence classes according to which ones are homeomorphic to one another. All right? That's what I meant when I said these are the categories of homeomorphic sets. They are really, technically speaking, equivalence classes of homeomorphic things. But we never actually talked about whether or not this relationship, the homeomorphism, is an equivalence relation. If you want to make equivalence classes, it has to be an equivalence relation. So this is a bit of perhaps a preliminary technicality. I didn't want to talk about it before, but really, technically speaking, we should have already been talking about that, because here I'm talking about classes which are equivalent according to homeomorphism. So I want to write this as a theorem. And it just says this relationship is an equivalence relation. And I have been like casually using this fact all along, although I don't know if anybody was objecting, but I have been using the fact that this is an equivalence relation as I've been talking about this. Let's see, this is not hard to prove, but we should try and do it. An equivalence relation, I hope you remember, there are 3 properties that need to be satisfied. Anybody remember the 3 properties of an equivalence relation? Those of you who took the comprehensive exam recently maybe reviewed this.
Symmetric, transitive, and reflexive.
Yes, reflexive, symmetric, and transitive are the 3 properties. And usually people talk about them in that order because that's sort of, that's from easiest to hardest generally when you're trying to prove something is an equivalence relation. So yeah, we'll show refl, sim, trans. Those are the 3 parts. Usually the transitivity is the pain. The other 2 are typically easier to discuss. Reflexive, symmetry, and transitivity. So let's talk about reflexive first. Anyone remember what that means? The reflexivity property of a relation? Yeah?
It's like flexible. It's equivalent to itself.
Yeah, something is equivalent to itself. So to show the reflexivity property for homeomorphisms, we need to show that X is homeomorphic to X, right? This is what you need. So how do we show things are homeomorphic? You need to create a function which has all the necessary properties. So we want some function f, x to x, which is a homeomorphism. That is to say, continuous bijection with continuous inverse. All right. Anybody want to suggest the function to use here? You want a function from x to x, which is continuous bijection with continuous inverse. Yes?
Equals that.
Yeah, how about f of x equals x? This is also known as the identity function. You know, you can think of a homeomorphism as transforming one space into another, and this is a transformation which just doesn't do anything. It leaves everything the way it was. That is automatically continuous because, remember, continuous means the preimage of an open set is open. So if I take U is an open set and I do the preimage of U using the identity function is just U again, and so it's still open. All right, so the identity function, it's also automatically a bijection because its inverse is itself. This is a homeomorphism. I don't think we need to write the details. It's a homeomorphism because it's a bijection and it's continuous and the inverse is continuous. Actually, the inverse is the same function again. Okay, so that's the reflexivity property. This is a homeomorphism as desired. So x is homeomorphic to x. All right, that's the reflexivity. What about symmetry is the next one. Anyone recall what does the symmetry mean? Yeah?
If x is equivalent to y, then y is equivalent to x.
Right, so in this case I want to show x homeomorphic to y implies y is homeomorphic to x. All right, so we assume that x is homeomorphic to y, and then we need to create a function which goes from y back to x. Now, the fact that x is homeomorphic to y, I can say that means so there exists a function f from x to y, and f is a homeomorphism. What I want is a function going back the other way because we need to show that y is homeomorphic to x. So anyone suggest what is a function which goes from y back to x? Yeah?
The inverse.
Yeah, f inverse. How do you know that f has an inverse?
It's a bijection.
Yeah, because I said it's a homeomorphism, which automatically means it's a bijection. So f does have an inverse. So I will just say since f is a homeomorphism, we can use f inverse, right? And f inverse has the proper, no, I wrote it wrong. It's y to x, that's the point. F inverse goes y back to x. Is F inverse also a bijection? This is like a basic fact from discrete math. If you have a bijection, the inverse is also a bijection. It is. And is the inverse also continuous? And like what we need, so this, I will just say, is a bijection. F inverse, and so this is maybe slightly confusing, but to show it's a homeomorphism, you have to show that this function is continuous and also the inverse of this function is continuous. So F inverse and F inverse inverse, those are what we have to show are continuous. These are continuous though, since, how do we know F inverse is continuous? Yeah? Yeah, since we already said F is a homeomorphism, that means that F inverse is continuous. So that one is continuous. What about F inverse inverse? That, my friends, is F. And that's also part of F being a homeomorphism, is that F inverse inverse, this is F. These are continuous since F is a homeomorphism. All right, so that'll do it. That means that F inverse is a homeomorphism, so Y is homeomorphic to X. Excellent. That's the symmetry property. And finally, the one that is usually the hardest is the transitivity. Anyone remember what's the transitivity setup? Yeah.
If x is equivalent to y and y is equivalent to z, then x is equivalent to z.
Right. So if x is equivalent to y and y is equivalent to z, then x is equivalent to z. All right. So this one is usually the most complicated to write the proof, but it's not any harder in this example. We assume that x and y, there's a homeomorphism from x to y. So we assume there exists f x to y, a homeomorphism, and also g y to z, a homeomorphism. And we need to create a function x to z. That's the conclusion. We can use, fill in the blank. It's got to go x to z. Anybody, how should we create a function from x to z? Yeah?
We can do like a composition.
Yeah, composition. Should it be f circle g or the other way around?
The other way.
This is the hardest part.
G circle F.
G, yeah, it should be G composed with F. That way the F happens first so that the domain is X, and then the G happens and you end up in Z. All right? Is this really a bijection? So again, this is a fact from discrete math. This is true of any functions. The composition of two bijections is also a bijection. That's a fact. Is it also continuous? Is it true that if you have two F and G are both continuous, does that mean that this is continuous? The answer is yes. We talked about that last time maybe, or 2 times ago. That was one of our basic theorems about continuous functions. And what about the inverse? So let me just say G compose F is a bijection. Since F and G are bijections, and that's a fact about any functions. A composition of two bijections is a bijection. What about the continuity properties? G compose F is continuous since, come on now, since G and F are continuous. I have a problem. I don't know if you noticed. I just did it twice. Whenever I write since followed by G, I write singe, which is not right. Since G and F, yeah, G composed with F is continuous since G and F are each continuous. And what about the inverse? G composed with F inverse. This one maybe you have to think a little bit about. I would like to just say this is continuous since G inverse and F inverse are continuous, although this isn't really, I'm not talking about G inverse and F inverse here. I'm talking about G composed with F inverse. Can you make is there some connection of this related to G inverse and F inverse? Yeah.
Isn't it f inverse equals G?
Yeah, this is F inverse composed with G inverse. And now you can say that's continuous because each of those things is continuous. So this is continuous since F inverse and G inverse are continuous. All right, great. So that means G composed with F is a homeomorphism. So X is homeomorphic to Z. And now we can legitimately talk about the classes of things which are homeomorphic to one another, just like we were talking about before. This is a bit of a technicality that needs to be settled before you start talking about classes. All right. In our remaining 10 minutes, I think we can make a very slight progress on talking about how do you show two sets are not homeomorphic. This is, like I said before, at least from a theoretical point of view, this is going to be much harder because to show they are homeomorphic, you just have to write down a function. To show they are not homeomorphic, you have to somehow prove that there can be no function which is a homeomorphism, and that's quite a bit more difficult. But I want to say what's the purpose of a homeomorphism is that homeomorphisms act nice. I will say specifically what I mean by this. Act nice on open sets, right? So, for example, if f x to y is a homeomorphism, what that means is the fact that, first of all, that f is continuous. F is continuous. What that means is that u open implies f inverse of u is open. That's the definition of continuous, right? Now, if it's a homeomorphism, that means also f inverse is continuous. So f inverse is continuous. What that means is u open implies f inverse u is open, right? Which is a little strange, but that's what it would mean to say f inverse is continuous. The preimage using f inverse, all right? But of course, f inverse, the preimage of f inverse, that's the same as f when f is a bijection. That's the same as f. So really, this means, like this right here, this is the same as just saying f of u is open, all right? So another way to think about a homeomorphism is it's a function where it takes an open set to an open set, and vice versa. It takes an open set in the domain to an open set in the codomain, and also takes an open set in the codomain back to an open set in the domain. So another way to say this is that f is a homeomorphism means, first of all, it's a bijection, but in terms of the continuity and the open sets, it means u is open if and only if, or I'll write it with the, this guy, right? Both ways, f of u is open, right? Because that's what this says. U is open implies f of u is open, but also the other way around is true too. You can go the other way also. If you have an open set in the range, you can bring it back and it makes an open set in the domain. So u is open if and only if f of u is open. This is those two continuity properties of a homeomorphism written together. And what that means is that this is sort of the way that I usually think about a homeomorphism. So a homeomorphism, sort of like deep down in my heart, I don't really think about those three properties when I think of a homeomorphism: bijection and continuous and the inverse is continuous. That's true technically, and if I want to prove something is a homeomorphism, that's how you have to do it. But sort of on a spiritual level or deep down in my heart, when I think about a homeomorphism, it just makes an exact correspondence between all the open sets in Y, or in X, and all the open sets in Y. All right? It's just a function which transforms any open set from X into an open set from Y, and vice versa. It also, going the other way, transforms an open set from Y into an open set from X. And it does this in a bijective way. All right? So it's just, you could think of it as, it doesn't really change the open sets, it just like rearranges them or something. All right, it makes a correspondence between the open sets in X and the open sets in Y. What this means is, so any property of X defined using open sets must be the same for Y. For example, if X and Y are homeomorphic and X uses the discrete topology, that means every set of X is open, automatically Y must also have the discrete topology, because a homeomorphism is a correspondence between all the open sets from the one with all the open sets from the other. And if there is a homeomorphism, what you're saying is that the open sets from the first one is basically the same as the open sets in the second one. And so any property defined using open sets must be the same for Y. Of course, any property defined using open sets, this is basically like any topological property. If it is defined in terms of open sets, then it will be the same when two spaces are homeomorphic. If it's defined some other way, then a homeomorphism might not preserve that property. But homeomorphisms preserve any topological property. So very specifically, one thing I could write as I'll write this like a corollary. Actually, this is written as a theorem in the book, and they write a specific proof. But in my opinion, you don't really need to write a specific proof about this. It says if X and Y are homeomorphic, and let's just say X is Hausdorff, then Y is Hausdorff. All right. And what the proof would be, I'm not really going to write it, but what the proof would be is just to say that X being Hausdorff is some kind of a statement about how all the open sets of X are arranged. If you have 2 points, then there can be 2 open sets which are disjoint. If X and Y are homeomorphic, it means the open sets of Y are arranged in the same way as they are in X. And so Y automatically must also be Hausdorff. Basically, you could substitute, instead of this word Hausdorff, you could substitute any property which is defined in terms of open sets. And it must be true of the other one also. All right? If X is Hausdorff and they're homeomorphic, then Y is also Hausdorff. So this actually is a more common way to show that things are not homeomorphic, is by somehow demonstrating they have some different topological properties. So we can show that X is not homeomorphic to Y by demonstrating some specific topological property that's different. In X and Y. All right? For instance, if one is Hausdorff and the other isn't, then they can't be homeomorphic. That's one fairly workable way to show that two things are not homeomorphic. So for example, e.g., R is not homeomorphic to R with the finite complement topology. That's because R is Hausdorff, but that other one isn't. That's an example we talked about in the past. This is Hausdorff, but this is not Hausdorff. And so they cannot be homeomorphic. All right? Because the one is Hausdorff and the other isn't. And this is generally how you show that things are homeomorphic. Not so much, you don't use Hausdorff every time. You just have to think of some property that's different from the one versus the other. And if it's a topological property in terms of open sets, then it means they can't be the same. Here's another example that's not about Hausdorff. How about R versus R with the lower limit topology? They are not homeomorphic. Why not? You have to somehow think about some way in which the open sets from R are different from the open sets from R with the lower limit. Now, obviously, they look different, but you have to describe how maybe R has some different arrangement of open sets than the other one, all right? And it's not obvious what the difference is, but if you think about this, one thing that you can say about R and R with the lower limit is in R, the only clopen sets are R and the empty set. This is a basic fact about the standard topology on R. The only sets which are open and closed are the whole space and the empty set. Talk about that in real analysis. What about R with the lower limit? Actually, this is also examples we've done in the past. I don't remember, but in R with the lower limit, any interval, A to B like this, is clopen. That's because the complement of that also includes its lower limit. It would be B up to infinity and also minus infinity up to A. But it would be, the complement of this is also open. So in RL, any interval is a clopen. That means these cannot be homeomorphic because the first one has only 2 clopen sets. The second one has infinitely many clopen sets. And so they cannot be the same topologically speaking. So R and RL are not homeomorphic. You just have to think of some specific property that's different. And then that means as long as your property is about open sets and closed sets or whatever, that means they cannot be homeomorphic. All right, that'll do. Let me know if you have homework questions. I am going to be sitting in my office for the next hour, so I'm happy to talk about it now if you like.